How-To: Absurd Scientific Advice for Common Real-World Problems by Randall Munroe. Picture this. You're an engineer at NASA. Your team has just poured years of work into building Curiosity, a multi-billion-dollar, car-sized rover destined for Mars. Everything's ready to go, but now you're facing one final heart-stopping problem. How on earth do you land this priceless piece of equipment gently on the surface of another planet? The old tricks won't work this time. Parachutes and airbags that handled smaller rovers perfectly? Useless. Curiosity is simply too massive. The Martian atmosphere is paper-thin. Someone pitches the idea of mounting rockets directly on the rover to let it hover down smoothly. Sounds promising, except for one tiny detail. The rocket exhaust would kick up a blinding dust storm, making it impossible to see where you're actually landing. The team starts grasping at straws. And then, someone suggests an idea so outlandish, so completely bonkers, it sounds like something straight out of a Saturday morning cartoon. What if, they wonder aloud, we build a sky crane? Picture a separate rocket-powered vehicle hovering high above the Martian surface, lowering the rover down to the ground on a long rope, like a spider rappelling on silk. It sounds absolutely insane. It sounds like the kind of idea that gets you laughed out of the room. But as the engineers work through the math, something incredible dawns on them. Every single alternative is actually worse. So with the entire world watching and holding its breath, they go ahead and try the ridiculous idea. And wouldn't you know it? It works flawlessly. That single story perfectly captures the entire soul of the book we're diving into today. How-To: Absurd Scientific Advice for Common Real-World Problems. The author is Randall Munroe, who's a former NASA roboticist himself and the brilliant creator behind the beloved webcomic XKCD. This isn't just some collection of quirky facts or bizarre scenarios. It's genuinely a masterclass in creative thinking. It's a guide to looking at the simplest problems in our everyday lives. Things like jumping high, throwing a pool party, or crossing a river, and asking, what if we tackled this in the most complicated, inefficient, and scientifically fascinating way imaginable? By the time we're done here today, you won't just learn how to theoretically power your house by destroying one of Mars's moons. You'll also gain a fresh new lens for looking at the world around you. You'll discover that sometimes, by chasing down the most absurd ideas, we stumble upon the most profound truths about science, engineering, and the beautiful, intricate rules that make our universe tick. So let's jump in. At its core, this book is built on a wonderfully simple premise. We all start out not knowing how to do things. We learn the right way, the normal way, and usually we stop there. But Randall Munroe invites us to become explorers again, to look at a simple everyday task and let our curiosity run completely wild. What happens when we unleash the full power of physics and mathematics on problems that don't really seem to need them? Let's kick things off with something basic: moving your body. How do you jump really, really high? We watch basketball players soar through the air, but even the absolute best professionals can only jump about 2 feet straight up. Kind of disappointing, right? Our bodies have hard limits. If you want to go higher, you've got to cheat a little. Now, you could grab a ladder, but that's hardly what we'd call jumping. A more interesting way to cheat, as athletes figured out long ago, is pole vaulting. You might assume the magic is in that bendy pole, but actually it's not. The pole is just a clever tool for redirecting energy. The real secret to launching yourself high is your running speed. All that forward momentum you build up sprinting down the runway gets converted, through the pole, into upward height. In fact, you could achieve almost the same height by running up to a perfectly curved ramp on a skateboard. The physics are nearly identical. But how high can you really go? Pole vaulting maxes out around 6 meters. To soar higher, we need to cheat even more creatively. We need to get the planet itself to help us out. Imagine you're standing on the side of a mountain. Wind comes rushing toward the mountain and, with nowhere else to go, flows upward along the slope. This is called an updraft. Birds use gentler versions of this, called thermals, to glide for hours without ever flapping their wings. For a human, though, you'd need winds blowing upward faster than your terminal velocity. That's the speed you'd reach in free fall, about 130 miles per hour. We're talking hurricane-force wind shooting straight up. You won't find that on most mountains. But here's the clever bit. You can change your own aerodynamics. A wingsuit can reduce your falling speed to just 30 miles per hour. A paraglider can slow it down even further, enough that a strong ridge wind could actually lift you right off the ground and carry you thousands of feet into the air. But we're not shooting for thousands of feet, we're going for the record. In a handful of special spots on Earth, like certain mountains in Argentina, something remarkable happens. When conditions align just right, the mountain waves, those updrafts, can interact with the polar night jet stream, creating waves of rising air that reach all the way into the stratosphere. Back in 2006, two glider pilots, Steve Fawcett and Einar Enevoldsen, rode these stratospheric waves to over 50,000 feet. That's nearly twice the height of Mount Everest, higher than any commercial airliner flies. They only stopped because their pressure suits inflated so much they couldn't reach the controls anymore. So here's your recipe for achieving the highest jump in human history. You build yourself an outfit shaped like a sailplane, seal yourself inside, leap into the air from a windy mountain ridge in Argentina, and ride the wind straight into the stratosphere. You'll have jumped higher than any wing-borne aircraft in history. You won't get an Olympic medal for it, but you'll know deep down that you're the true champion. This approach, taking a straightforward goal and pushing it to its most extreme, logical conclusion, is the engine powering the entire book. And it's not just about moving your body through space, it's about moving your entire life. Consider the common headache of moving to a new house. The normal approach involves endless cardboard boxes and a rental truck. It's exhausting work. So much work, in fact, that you might be genuinely tempted to just dig a giant hole and shove all your belongings into it. That's technically an option, but what if you absolutely refuse to pack a single box? The alternative is elegantly simple. Move the entire house. People actually do this fairly often, lifting a house right off its foundation with steel I-beams and placing it on a flatbed truck. But here's a question physics can answer. What kind of gas mileage would your house get cruising down the highway? A house is about as aerodynamic as a brick. At 55 miles per hour, you'd be looking at roughly half a mile per gallon. At 80 miles per hour on the German Autobahn, you'd burn a gallon of gas every 200 feet, and the wind would likely start peeling important pieces off your roof. Driving seems too slow anyway. Why not fly? The world's most powerful helicopters can't lift a whole house by themselves. But what if you used several working together? The U.S. military actually studied this exact scenario during the Cold War, proposing a superlift vehicle made by essentially strapping two massive helicopters together. A better option turns out to be a cargo plane. A C-5 Galaxy has enough power to lift a medium-sized house, though it probably won't fit inside the cargo bay. You'd have to strap it to the top, similar to how NASA transported the space shuttle. On the plaque next to the shuttle mount on the carrier aircraft, there's perhaps the greatest joke in aerospace history. It reads, "Attach orbiter here. Note, black side down." But even strapping your house to a plane feels too conventional. Why use the whole plane at all? Why not just grab the engines? The engines on a 787 Dreamliner are powerful enough to lift a small house straight up into the air. With 4 of them strapped to the sides, you could transform your home into a giant, hovering drone. You could fly for roughly 90 minutes before needing to refuel, making any move under 100 miles totally doable. This beautiful escalation of absurdity, from jumping to moving to literally flying your house, reveals fundamental truths about energy and motion. But what about manipulating our environment on an even grander scale? Let's say you want to throw a pool party, but you've hit a small snag. You don't actually have a pool. Don't panic just yet. An in-ground pool is really just a fancy hole with some plumbing, so you could start there. An above-ground pool is even simpler, just walls and a floor. But here's the catch. Water is surprisingly heavy, and it pushes outward on the walls with a force engineers call hoop stress. If your walls aren't strong enough, they're going to burst spectacularly. So what should you build your pool walls out of? Aluminum foil? The math says you could only fill it 5 inches deep before it explodes outward. What about, and hear me out here, cheese, physics doesn't judge whether your question is weird. It just gives you the answer. According to a 456-page handbook called Cheese Rheology and Texture, hard Gruyere cheese has a specific tensile strength. Plug that into the formula, and you discover you'd need a 2-foot thick wall of Gruyere cheese to contain a 3-foot deep pool. As the book helpfully notes, you may have some trouble convincing anyone to actually jump in. Now you need to fill it with water. A garden hose takes forever. What about ordering water online? You could technically order 20,000 gallons of Fiji water from Amazon. This would cost you an absolute fortune and leave you staring at 150,000 bottles that need opening. Opening them one by one is painfully slow. What about using a sword? Also too slow. A shotgun? Way too messy. What about a nuclear bomb? This is a completely ridiculous suggestion, which is exactly why the U.S. government studied it during the Cold War. In 1955, they placed beer and soda bottles at various distances from a nuclear test site to see if the beverages would survive and remain drinkable. The conclusion? The beer mostly tasted fine and was perfectly safe to drink, but nuclear weapons, as it turns out, make terrible bottle openers. The most efficient solution is an industrial plastic shredder, which can process 30 tons of bottles per hour, shredding them open and filling your pool in just over 2 hours. But why stop at a pool? What if you need to cross an entire river? You could try swimming, but that can be legitimately dangerous. You could try jumping across it. A fast runner can clear a 7-foot gap. On a bicycle cruising at 30 miles per hour, you could theoretically jump a 60-foot river, but you'd also slam into the other side at 30 miles per hour, which is basically a recipe for a hospital visit. So maybe jumping isn't your best bet. What about changing the physical state of the river itself? You could freeze it solid. To create an ice bridge, just 4 inches thick and wide enough to be stable, you'd need about 330 megawatt-hours of electricity, costing around $50,000. And that's just for a temporary crossing. To freeze the entire flowing Kansas River would require 87 gigawatts of power, roughly the same energy output as a heavy-lift rocket at takeoff. Powering the refrigeration equipment would require a literal river of gasoline, nearly 5% the size of the actual river you're trying to freeze. Freezing is clearly impractical, so let's flip to the opposite approach, boiling it. Could you install enough electric tea kettles upstream to turn the entire river into steam? letting you casually walk across the dry riverbed? To boil the Kansas River, you'd need 300 million electric tea kettles running simultaneously, covering a circular area 2 miles across. The power draw would equal the entire electrical grid of the United States. Plugging it all in would blow every circuit breaker in the state. But if you somehow could power it, the result would be genuinely apocalyptic. The rising steam would form a mushroom cloud, reaching the stratosphere. The heat radiating from those kettles would exceed a miles-wide lake of molten lava. In fact, as the book wisely points out, anything that puts out as much energy as a lake of lava becomes a lake of lava. Your kettles would melt into a bubbling, molten disaster. So if we can't go over the river or through it, perhaps the best solution is also the most elegant. When engineers needed to build the first suspension bridge over the Niagara Gorge, they couldn't get a boat across the violent, turbulent water. Instead, they held a kite-flying contest, offering a cash prize to whoever could fly a kite from one side to the other. A 15-year-old boy named Homan Walsh succeeded, and his thin kite string was used to pull a slightly stronger rope across, then an even stronger one, and eventually the first steel cable of the bridge. This pattern of finding a simple underlying principle and applying it in increasingly extreme ways is a theme that keeps popping up. It even applies to everyday actions like throwing objects or playing musical instruments. This same spirit of boundless expansion applies to the chapter on how to play the piano. A standard piano has 88 keys, covering most of the range of human hearing. But why stop there? To play all the notes a young child can actually hear, you'd need to add 27 extra keys on the high end. Dogs can hear even higher frequencies, requiring another 12 to 15 keys. Bats, which use ultrasound for echolocation, would need several more keys still. On the low end, elephants can hear infrasound, frequencies below 20 Hz, so you'd need another 5 keys on the left side. The absolute lowest frequency sounds, called microbaroms, are generated by massive waves rolling across the open ocean, the planet's own deep subwoofer. To play that ancient music would require another 75 keys. Your final piano would have 235 keys in total, capable of playing everything from Beethoven to bat-hunting songs to the haunting voice of the sea itself. This relentless questioning leads to one of the most entertaining and yet oddly practical sections of the entire book, a question-and-answer session with Colonel Chris Hadfield, a real-life astronaut and test pilot, on how to handle various emergency landings. If you have to land a small plane in a farm field, what crop should you aim for? Hadfield's answer comes without hesitation. A freshly planted field is your best bet. The absolute worst is one that's just been plowed into furrows. Whatever you do, avoid sunflowers at all costs. What if you have to land a normal passenger plane on an aircraft carrier? Simple. Get the captain to turn the ship into the wind and gun the engines as fast as possible. This creates a 50 or 60 mile-per-hour headwind, dramatically slowing your speed relative to the deck below. What if you're somehow locked out of the plane but can crawl around on the exterior? You can't move the main control surfaces by hand. They're way too stiff. But, Hadfield explains, if you're clever, you can locate the small trim tabs on the edge of the tail fins. These are used for tiny adjustments and are small enough to move by hand. By carefully manipulating them, you could, at least in theory, actually fly the plane down to a safe landing. Perhaps the most absurd question in the entire exchange is this. You're sitting inside the space shuttle while it's being carried piggyback on its 747 carrier aircraft. Suddenly, the pilot of the 747 bails out mid-flight. What do you do? Hadfield's answer: delivered without even a moment's hesitation, is beautifully simple. Fire the separation mechanism, pull back firmly to clear the carrier's tail, and then glide to a landing. Easy peasy. The scenario sounds like something from an action movie, but it's actually how the shuttle's very first test flights were conducted. What sounds like desperate improvisation is, to an astronaut, just standard operating procedure. The book is absolutely packed with these moments where an absurd problem suddenly reveals a deep and often surprisingly simple truth. Can you power your house if you're living on Mars? Not easily, unfortunately. The wind is too thin and the sun is too far away. But Mars has a tiny moon called Phobos that's slowly spiraling closer to the planet. In theory, you could attach a 800-kilometer tether to it, letting the end dangle down into the Martian atmosphere. As Phobos whips around Mars, the end of the tether would slice through the thin air at over twice the speed of sound. A turbine attached to that end could generate enough electricity to power an entire town. The drag would gradually pull Phobos closer, but in the process, you could power a Martian civilization for thousands of years, right up until the moment the moon finally crashes into the planet, causing a dinosaur-level extinction event. Free energy, it turns out, often comes with a terrible long-term price tag. Ultimately, How To isn't actually a manual for doing things the wrong way. It's a joyful celebration of curiosity. It's a testament to the idea that no question is too ridiculous to ask as long as you're willing to follow the science wherever it leads. Whether it's figuring out if you're a 90s kid by checking for radioactive isotopes in your teeth from Cold War bomb tests, or winning an election by legally changing your name to above's known of the, so you appear first on the ballot, Munroe shows us that the world is essentially a giant playground of interconnected systems, all governed by elegant rules. And the more we play around with those rules, the more we understand not just how the world actually works, but how we can think more creatively, solve problems more effectively, and never, ever lose that precious sense of wonder. As we reach the end of our journey through How To, it's worth pausing for a moment and asking ourselves, what is this book really trying to tell us? On the surface, sure, it's a collection of brilliantly funny, wildly impractical solutions to everyday problems. It's a book that makes you laugh out loud while sneakily teaching you about fluid dynamics or orbital mechanics. But underneath that playful exterior lies something much deeper and more valuable. This book is essentially a love letter to the process of thinking itself. In a world that constantly rewards quick answers and safe, conventional wisdom, Randall Munroe champions the slow, deliberate, and often beautifully messy process of figuring things out from first principles.